Deployed machine learning systems consistently solve search-oriented tasks with vast, long horizon spaces, problems traditionally treated as computationally intractable. Success in these domains rarely comes from a single forward-pass prediction. Systems like AlphaGo rely on a specific architecture of search and evaluation rather than an instantaneous answer. In technical fields like Olympiad geometry, models now use inference time scaffolds. They operate in loops, proposing a solution, critiquing the logic, and repairing errors over multiple stages before settling on an output. This empirical progress creates a tension in classical theory. Some observers argue these results imply hard problems are becoming uniformly easy. Others contend that once a system relies on multi-agent loops and repair cycles, classical complexity theory no longer applies. Deployed systems operate on the same frontier that made the study of P and NP foundational, the gap between the ease of verification and the difficulty of direct construction. We require a mathematical vocabulary designed specifically to measure progress on that frontier. This framework translates engineering practices into formal complexity theoretic definitions, moving from loose descriptions to rigorous objects. An end-to-end predictor functions as a direct polynomial time decision algorithm, placing it in the classical class P. A multi-agent debate and repair loop represents a bounded guided verification protocol, which sits within the tiers of the polynomial hierarchy. The entire deployed pipeline is formalized as a deployed stage, or S, the specific bounded artifact that engineering practice actually puts into production. Within this model, increasing test time compute constitutes an expansion of a bounded resource budget rather than a structural change to the system's architecture. Mapping these workflows to formal logic allows us to distinguish between raw compute scaling and genuine structural advancement. In the baseline regime of Class P, a single bounded deterministic procedure returns an answer without the need for auxiliary witnesses or external subroutines. Class NP widens this access by allowing for efficient verification. A yes instance may lack a direct polynomial time construction, yet a bounded witness can certify success in polynomial time. The polynomial hierarchy extends this logic by adding layers of proposal, challenge, and repair. Each level adds a bounded interaction stage before the final efficient check. This maps to common AI workflows. A system proposes code at line 1, receives a critique at Y2, and produces a repaired program at Y3. By recording how these richer interaction patterns become internal to verification, the polynomial hierarchy provides a structural model for multi-stage reasoning scaffolds. To measure progress, we bundle these into a deployed stage. First is the core, the fixed inner engine, defined by its verification depth. Surrounding it is the exposure interface, receiving bounded passive data, like retrieved text. The deployed stage remains an immutable protocol family. It is a set of fixed bounds, regardless of the specific prompt or execution trace. These structural limits allow us to separate the native internal capabilities of the model from the external data and tools it processes. Fixing the stage architecture projects two distinct mathematical boundaries of capability. The native reach defines problems the stage solves using only its internal resources. The closure frontier marks the absolute limit achievable using any exposable support. The native reach is mathematically constrained by this outer boundary. True structural progress requires a system to escape this boundary. To move past the closure frontier, the architecture itself must change. When an updated model shows improved benchmark performance, the question is whether that improvement represents a new paradigm or a simple optimization of the current one. Pumping more compute or more iterations into the same search process expands the native reach, but the system eventually hits the rigid limit of the closure frontier. This budget expansion fills the existing capability gap. It produces better results, but it leaves the mathematical frontier of the stage unmoved. We see a similar effect with internalization. This occurs when tool outputs or construction steps that were previously provided via external transcripts are baked directly into the model's weights. Alpha Geometry 2 improved on its predecessor by internalizing the construction support that the original system required from an external symbolic engine. Budget scaling and internalization improve efficiency and reach, but the system remains trapped within its original closure frontier. Escaping the closure frontier requires three mathematical routes. First, deeper bounded verification adds a new layer of challenge or repair. Second, stronger core authority replaces the engine with a more powerful verifier. Third, witness set expansion allows the interface to process radically richer supporting artifacts. These three branches, depth, authority, and expansion, provide the only mathematically sound definitions of structural progress in modern AI. The stage descent framework replaces shifting empirical benchmarks with mathematical invariance. We can now decouple financial computing budgets from architectural leaps. Defining the closure frontier clarifies what a model can do natively versus what it achieves through the support of its environment. Inference time scaffolds and multi-agent loops sit at the center of classical complexity. They represent the practical application of efficient verification to solve difficult problems. These systems return to the mathematical frontier of P versus NP. Complexity theory provides the ultimate blueprint for the future of artificial intelligence.